Allora, nelle slide che avevo messo la volta scorsa, in coda avevo anche messo questi testi di questi problemi che vedremo oggi. Per caso qualcuno di voi ha provato a risolverli? Allo? C'è qualcuno?
No, mi spiace, io non...
Va bene, va bene.
Sì, scusi. No, io mi spiace.
Ok, li facciamo adesso insieme. Allora, cominciamo dal primo e adesso alterneremo quindi la slide per leggere il testo e poi la lavagna per risolverlo. Allora, iniziamo quindi col 2.1. Using JPC omega 1 minus minus, check the conservation of P of parity and charge conjugation in the decay omega into pi plus pi minus. Ok, quindi usciamo da qui, andiamo sulla lavagna. E iniziamo a risolvere questo problema. Quindi questa è la pagina 1 e il problema è 2.1. Quindi sostanzialmente il testo ci dice che i numeri quantici della omega, scritti in questo modo, sono j omega pc uguale 1 meno meno. Quindi passo all'inglese adesso. So this means that the total angular momentum is 1, so j is 1, then the parity eigenvalue is -1, and the charge conjugation eigenvalue is -1. So we want to check conservation of parity and charge conjugation in the decay omega that goes into pi plus, pi minus. Okay, so let's start analyzing what we know from the text. So first of all, we know that the total angular momentum in the initial state is the total angular momentum of the omega meson, that is 1, okay, as we know from the text. So by angular momentum conservation, we know that also the final state total angular momentum must be also 1. That is the angular momentum of the pion pairs that we can split in the orbital angular momentum plus the spin of the pion pairs. And this must be 1 in order to ensure angular momentum conservation in the process, in the decay process. Okay. Now we also know that the pions are spinless mesons, so pseudoscalar mesons. That means that they come with spin equals 0. So for sure we don't have this contribution here, and we can immediately say that the orbital angular momentum of the final state system must be equal to 1. Okay, and this comes just from angular momentum conservation in the decay. Now, what about the parity? So the initial parity pi is the parity of the omega, and we know from the text that this must be -1. What about the final state parity? So the p in the final state is the parity of the pion system. That is, as you remember from the last lesson, -1 L pi pi times the intrinsic parity of the two pions. And since pions are pseudoscalar mesons, they both come with negative intrinsic parity. Okay, so we have a +1 coming from here. L is equal to 1, so this is equal to -1 to the 1. So overall, this is -1. Okay, and in fact, it is equal to the initial state, so to the P of the omega. So parity is conserved in this decay. What about now charge conjugation? Again, from the text, we know that the initial state charge conjugation eigenvalue is -1. In the final state, we have the charge conjugation of the two pion system. Okay, and since the pions are spinless bosons, if you remember from the last lesson, this must be equal to -1 L to the pi pi. Okay, so we don't have here to include the asymmetry of the spin component of the wave function because pions are spinless bosons. Okay, so this is -1 to the 1. That is also -1. That is so coincides with the initial state charge conjugation eigenvalue, and so we can also claim that charge conjugation is conserved. Chiaro? Ok.
Sì, per me è chiaro.
Ok, molto semplice. Facciamone un altro, diciamo anche questo qui è abbastanza semplice, quindi torniamo adesso alla slide. Allora, il problema 2.2. The psi prime meson is a 2s13 CC bar state. Calculate its JPC quantum numbers. Quindi questo è un po' il problema inverso. Si vuole calcolare adesso i numeri quantici nella combinazione JPC, che è il modo standard per rappresentare i numeri quantici di hadroni e barioni, e di barioni e mesoni, e quello che ci viene dato è la notazione spettroscopica. Okay? Quindi da quell'informazione 2S13 dobbiamo ovviamente risalire quelli che sono poi i numeri quantici sostanzialmente di momento angolare e spin. Okay? Il mesone psi', come studieremo, è uno degli stati del cermonio, quindi di fatto è uno stato eccitato di un sistema legato quark C barra, charm anti-charm. Ok, quindi torniamo indietro di nuovo sulla lavagna. Cambiamo pagina. Ok, quindi questa è la pagina 2 e questo è il problema 2.2. Okay, so in general the spectroscopic notation is in the form N, L, J, 2s plus 1. This you know already from atomic physics, okay? I'm sure you know this already. So in our case, this takes the form 2s3 1. So by comparison, okay, we don't care about the n, the principal quantum number, but what we care about is L and S. Okay, so what we learn from this is that L is equal to 0 because it is in S wave. Okay, so the capital S means S wave that corresponds to L equal to 0, as you know. The spin, okay, must be 1 in order to get to 2s plus 1 equal 3. And therefore, J is equal L plus L must also be 1. So let's calculate now the parity of this psi prime meson. This is -1 to the L of the C bar system. So it is a system, a bound system of quark and anti-quark. So we have to multiply this by the intrinsic parity of the charm quark and by the intrinsic parity of the anti-charm quark. Now, this is equal to -1 of the L psi prime, of course. And then the intrinsic parity of quarks, if you remember, by convention are positive, and the intrinsic parity of anti-quarks are negative by convention, okay? So we get a minus sign from here, and then this is so equal to -1 to the 0 times -1, that gives us -1. So the parity of the psi prime is negative, -1. What about now the charge conjugation? Okay. So this is given by -1. If you remember, for a pair of fermions, this is given by LCC bar plus SCC bar, because in this case, you have to take into account also the symmetry of the spin component of the total wave function. Not only the spatial component, but also the spin component, because, of course, quarks are fermions, so they come with spin 1/2. And so this is -1 L of the psi prime plus S of the psi prime. That is -1 to 0 plus 1. And so this is -1. And so we can now put all the information together. We know that the total angular momentum is 1 from here. We have calculated the eigenvalues of parity and charge conjugation, and therefore the quantum numbers J psi Pc can only be 1 minus minus. Okay? Let's now move to the next problem. Se avete domande, ovviamente fermatemi e chiedete.
No, finora tutto.
No? Ok. Andiamo al 3. So find the possible values of JPC for a system made by a spin 1/2 particle and its antiparticle if they are in an S wave or in a P wave state. Ok, questo è un attimino più elaborato come esercizio, quindi torniamo nuovamente sulla lavagna. Ok. Quindi questa è la pagina 3. Come avete visto, le scansioni, diciamo, di queste cose che vi sto scrivendo le trovate, anche queste qui ve le metto online in formato PDF. Quindi, problem 2.3. So let me read again the text. So find the possible values of JPC for a system of a spin 1/2 particle and its antiparticle if they are in an S wave or in a P wave state. Okay. So we are now dealing with a pair of fermions, actually a fermion and an antifermion, both with spin 1/2. So the total spin can be essentially in two states for the pair. So either S equals 0, which is a singlet, or S equal 1, as you know, it corresponds to a triplet. Okay. So let's start from the first request. So when the system is in an S wave, that means that the orbital angular momentum must be 0. So what about now the total angular momentum? So J is equal to L plus S. And so we have here two possibilities. If S is equal to 0, then also J is equal to 0, because L is equal to 0. If S is equal to 1, then J must be also 1. And so now if we translate this into the spectroscopic notation, okay, we have L, J, 2S plus 1. That corresponds to, in this case, S, because we are in an S wave, 1, because the spin is 0, and 0, because the total angular momentum is 0. Whereas in this case, Lj 2s plus 1 corresponds to S, because we are still in an S wave, but now the spin is 1, and so also the total angular momentum is 1. Now, let's calculate now the parity and the charge conjugation of this system of fermion and antifermion. So the parity of fermion-antifermion pair is given as usual by -1 to the L of the system times intrinsic parity of the fermion times intrinsic parity of the antifermion. So we are in an S wave, so L is equal to 0, so we have -1 to the 0. And then by convention, you know that this is +1 for the fermion and -1 for the antifermion. So we get a minus sign here, we get a plus sign there, so overall this is -1. Okay, and these results only depend on the value of L, so on the orbital angular momentum. We don't care about the spin. So we have the same results for both situations, for both spin states. Differently, we will gonna have two different results for the charge conjugation. So let's start with CFF for the state 1s0. In this case, as we have seen last time, because we have now a system of fermion-antifermion, the charge conjugation eigenvalue is given by -1 L plus S. So again, we have to take into account not only the symmetry of the spatial part of the wave function, but also of the spin part of the wave function. So this is -1, 0 plus 0, that is +1. Whereas for the other state, we have CFF bar 3S1, that is -1 L plus S, but in this case, we have -1, 0 plus 1, because this corresponds to the triplet, and so this results in -1. So overall, our result is that JPC for the 1s0 state is 0 minus plus, and the JPC for the other state, 3s1, is 1 minus minus. Okay, very simple. Now, this was the first part. So in case the fermion antifermion pair are in an S wave state, let's now consider the second case where they come in a P wave. Quindi cambio foglio. Ok, quindi questa è la pagina 4 e questo è il caso B. So in this case, our system is in a P wave. That means L equal to 1. So let's repeat the exercise. Now J is equal to L plus S. So when S is equal to 0, so in the singlet state, J can only be 1. And so our state LJ2S plus 1 will be 1P1. On the other hand, when S is equal to 1, so we are now considering the triplet spin state, then we have to be careful when we couple the orbital angular momentum and the spin, because you know from quantum mechanics that we have three possibilities, either 0, 1, or 2. And so here we're going to have three different states, Lj to S plus 1, that are P0, 3, P1, 3, P2, 3. So spin is always 1, okay? So the upper number is always 3. We are still all states are in a P wave, so we have P everywhere, but then what changes is the total angular momentum, which is either 0, 1, or 2, depending on how you couple this angular momentum. So let's now repeat the exercise. So we start calculating the parity of the fermion-antifermion system. It is -1 to the L times intrinsic parity of the fermion times intrinsic parity of the antifermion. In this case, we are in a P wave, so this is -1 to the 1, and then, as usual, +1 times -1. So this is a minus sign, then we have another minus sign, so this is +1. Again, parity depends only on the value of L, so it is the same for all these states here. What about now the charge conjugation? FF bar. So for the state, let's start with the 1p1. Okay. So this is in general -1 L plus S. That is -1, 1, because we are in a P wave, plus 0 because this is for the singlet case. And so this is -1. Now for the other three states, CFF bar. So let's start with 3P0. This must be the same for CFF bar for the 3P1 and also the same for CFF bar for the 3P2 because they come with the same assignment of orbital angular momentum and spin. So for all three cases, we have -1 L plus S equal to -1, 1 plus 1. That is +1. So overall, we can now represent our results as JPC for the 1P1 state equal to 1 plus minus, and then JPC for the 3P0 state is going to be 0 plus plus. JPC for the 3P1 state is going to be 1 plus plus. And finally, JPC for the 3P2 state is going to be 2 plus plus. Okay, so parity and charge conjugation are positive everywhere in this second case, but what changes is the total angular momentum, J. Okay. Allora, andiamo al problema successivo. Problema 2.4. Calculate the quantum numbers P and C of the neutral mesons in two cases. So in one case is the row 0 meson with the mass 770 MeV. J is equal to 1 and the decay width is 149 MeV. And the F20 meson, the mass is higher, is 1270 MeV. J is equal to 2 and the decay width is 185 MeV. Both decaying into a pi plus, pi minus pair. So let's come back here. Questa è pagina 5. Problem 2.4. Okay. Let's start with the first case, so the row 0. So let me just write down again the data. J equal 1 and gamma 139 MeV. So what we can learn from this information, essentially, what is the decay width? If you remember, for any decay process, we can associate a mean life, so a decay time, which is the inverse of the decay width. So if we represent, for instance, the invariant mass of the pi mesons, pi plus, pi minus mesons, we will find at a certain point a resonance, and the width of this resonance is exactly gamma, the decay width. Okay. So as we've seen in the theory, okay, from the uncertainty principle, we know in general that delta E times delta T is order of h bar divided by 2. So in our case, we substitute delta E with half of this decay width. So gamma half. We substitute delta T with the decay time tau, and this must be of the order of h bar divided by 2. And so we obtain here that gamma times tau is of the order of h bar. And so the decay time of the row 0, okay, has to be given by h bar divided by the decay width of the row 0. The trick here is to multiply both numerator and denominator by the speed of light. So h bar c divided by gamma c. And the reason for that is that h bar c is a universal constant which is easy to remember, okay? It is 197 MeV times Fermi, but you can also use 200 here, it's fine, okay? It is even easier to remember. So 200 MeV per Fermi. And then on the denominator, we have 139 MeV times the speed of light in Fermi per second. So 3 10 to the 23rd Fermi per second. Okay. So once you do this calculation here, you obtain something like 4.4 10 to the minus 24 second. Okay. So an extremely short decay time. So now a question for you. What kind of interaction can regulate this decay? Can somebody tell me? Given this short decay time.
The weak interaction.
The weak is very slow, in the contrary.
The strong interaction.
The strong interaction, yes. This we will study, of course, even more later in the course. So when you have decay time of the order of 10 to the minus 23, 24, sometimes even 25, then this is for sure a strong decay, okay? We have exceptions also for the weak interaction, but in this case, like the decay of the Z, etc., of the top quark. But when you have a meson or a baryon decaying with such a short decay time, this must be a strong decay, or if you like, a decay regulated by the strong interactions, okay? Now, as we've seen, last time, okay, we know that both electromagnetic and strong interaction conserve parity and charge conjugation. These two observables are only violated by the weak interactions. So in this case, since it is a strong process, we expect that P and C must be conserved, because it is a strong decay or a strong process in general. Okay, so it must be conserved in the process in rho 0 that goes into pi plus, pi minus. Okay. Of course, also angular momentum must be conserved in the process. So let's now try to calculate the quantum numbers. So the angular momentum of the rho 0 in the initial state is +1, as we know from the data of the problem, okay, from the text. And so, of course, we have to enforce angular momentum conservation. So also the angular momentum of the final state, so the pion pair, must be equal 1. This, as usual, we can in general split in the orbital part and the spin part, and this must be equal to 1. Now, again, pions are spinless mesons, pseudoscalar mesons, so the spin contribution is 0. And so we learn from here that L pi pi must be 1, and so these two, the pion system is in a P wave. Okay, now we know everything. We can calculate. So this is, sorry for the, yeah, okay. So the parity of the rho 0 meson must be equal to the parity of the pi pi, because it is a strong decay, so parity must be conserved in the decay. And so this is -1 to the L pi pi times intrinsic parity of the pi plus times intrinsic parity of the pi minus. That is -1 to the 1, because we just derived that the orbital angular momentum must be equal to 1. And then both pi plus and pi minus are pseudoscalar mesons, so they come with both with negative intrinsic parity. And so we get a plus sign here and a minus sign there, so this is overall -1. Now let's work out the charge conjugation of rho 0, C pi pi, again for charge conjugation conservation in the strong decay. That is now -1 L to pi pi. And again, this is because pions are spinless, so we don't have to care in this case about the symmetry of the spin component of the wave function. And so this is simply -1 to the 1 or equal to -1. And so now when we put all these together, we obtain the quantum numbers, the APC of the rho 0 to be 1 minus minus. Okay, this was the first case, the rho 0. Let's now repeat the exercise for the second case, for the F20 meson. So I will now take a new page. Allora, questa è la pagina 6 e questo è il caso B. So the data are F20, 1270 MeV. This is the mass. This is the way one express the name of the meson. So you specify the symbol and also the mass in general. Then J equal to 2, and then the decay width is 185 MeV. So we do the same reasoning as before. So we calculate the decay time of the F20, that is h bar c divided by gamma c. That is again 200 MeV per Fermi, or if you want to be more precise, 197 MeV times Fermi. And then on the denominator we have 185 MeV times the speed of light, 310 to the 23rd Fermi per second. And the result of this is 3.5 10 to the minus 24 second. So clearly, again, this is a strong decay. And so again, we have to enforce and ensure that both parity and charge conjugation are conserved, in addition to the angular momentum, of course. So the initial angular momentum, so the angular momentum of the F02 is equal to 2, as we know from the text. And so also the final state must be equal to 2. So L pi pi plus S pi pi must be equal to 2. Again, the spin component here is 0 because we are talking about pions. And so it turns out that L pi pi is equal to 2. So this is a D wave, if I'm not wrong. And so now the parity of the F20 meson must be equal to the parity of the final state, so the parity of the pi pi system, that is minus 1 L pi pi times intrinsic parity of both pions, which is negative. And so this is essentially minus 1 to the second times 1, so this is plus 1. Concerning the charge conjugation, F20, this must be equal to the charge conjugation of the final state, that is minus 1 L pi pi only, that is minus 1 to the second, and so also here plus 1. And so overall we can write our result as JPC of the F20 as 2 plus plus. Ok, tutto chiaro ragazzi?
Ok.
Sì, chiaro.
Ok. Allora andiamo adesso al problema successivo. Problema 2.5. Calculate the value of Cp for a system of 2 neutral pions in an S-wave and for a system of 3 neutral pions. Quindi qua chiede di calcolare adesso il prodotto C per P, quindi il risultato dell'azione combinata in successione di coniugazione di carica e parità. Per due casi, anche qua un sistema di 2 pioni neutri in onda S e 3 pioni neutri. Vediamo poi come risolvere il secondo punto, che è un po' più complesso. Allora, torniamo qui. Siamo alla pagina 7. Problem 2.5. Allora, so we start with point A. Okay, so system of 2 neutral pions in an S-wave. So S-wave means that L pi pi is equal to 0. So we can already calculate the parity P of the pi 0 system as minus 1 to the L pi pi times intrinsic parity of the pi 0 times intrinsic parity of the pi 0. That is minus 1 to the 0 times minus 1 times minus 1. That is, of course, plus 1. What about now charge conjugation? So if you remember, the pi 0 is one such particle that is neutral, and it is a boson, and it corresponds to its own antiparticle. So it is an eigenstate of the C parity operator. So as we've seen last time, C over the pi 0 gives us plus 1 over pi 0. So in other words, the pi 0 is an eigenstate of charge conjugation with eigenvalue plus 1. So if we now want to calculate the charge conjugation of the pi 0 system, since it is a discrete symmetry, so a multiplicative quantum number must be conserved, this is going to be the product of the charge conjugation of each of the two pi zeros, that is plus 1 times plus 1, that is plus 1. And so now when we take the product, we obtain that the Cp of the pi 0 system is plus 1 times plus 1, so equal to plus 1. Okay. We can also make a check here, because we know that the 2 pi 0 are two identical bosons. So the overall wave function of the 2 pi 0 system must be symmetric under exchange. So if we can check if this is the case. So if you remember, in order to check these, we have to check that the symmetry of the spatial term times the symmetry of the spin term of the wave function, okay, this product must be positive for a symmetric wave function. So this comes from the symmetry of the spatial component of the wave function. This comes for the spin component for the case of bosons. Okay, this you find in the last part of 2 lessons ago. And so we have minus 1 to the 0 times minus 1 to the 0, and in fact this is plus 1. So as expected, the wave function is symmetric for exchange of identical pi zeros. Now, let's work out now the case B. Okay. So concerning, let's first calculate here the charge conjugation of the 3 pions system, pi 0, pi 0, pi 0. Okay. Again, the pi 0 is an eigenstate of C with eigenvalue plus 1. So this is just a plus 1 to the third, that is plus 1. What about now the parity? The parity of the pi 0, pi 0, pi 0 system. Okay, if you remember, now we are in the situation where we have 3 objects. So the pi 0, the other pi 0, and the other pi 0. So we're going to have an relative orbital angular momentum L12 between the first two. And then we're going to have the L3, that is the angular momentum of the third pion respective to the center of mass of the other two. This is in general for a system of 3 particles. So when we calculate the parity here, we're going to have minus 1 L12 plus L3 times the intrinsic parities of the 3 pi zeros, pi 0 and pi 0. That is minus 1 L12 plus L3 times minus 1 to the third, because always pions are pseudo scalar mesons, so they come with negative intrinsic parity. And so overall, this is minus 1 L12 plus L3 plus 1, because we have an additional minus sign here. What about now the combination of C and P together? So Cp of the pi 0, pi 0, pi 0 system is now given by the product. So this is a plus 1 for the charge conjugation and minus 1 L12 plus L3 plus 1 concerning the parity. So the plus 1 from the charge conjugation is irrelevant, in the sense that overall the Cp is given by the parity. So is L12 plus L3 plus 1, because the charge conjugation is a plus sign, so it doesn't add anything. So here we can split in 2 cases. So this is going to be plus 1 if L12 plus L3 is odd, or minus 1 if L12 plus L3 is even. So what we can use here to disentangle the two, this ambiguity. Provate a pensarci un attimo. Cosa possiamo sfruttare qui per capire quale delle 2 soluzioni è quella giusta? Nessuna idea? Ci siete, vero? O non sto parlando da solo?
Ci siamo.
Sì, io ci sono e sto provando a riflettere.
Ah, vabbè, vi lascio qualche secondo. Sì, vabbè, pensateci un attimo. Quindi abbiamo 2 potenziali risultati, ovviamente uno solo sarà quello corretto. C'è qualcosa che dobbiamo sfruttare per decidere quale dei 2.
non so, io pensando a un decadimento, cioè mi viene da pensare a un decadimento e penso alla conservazione della quantità di moto, però qua abbiamo un'interazione, giusto? Non un decadimento in tre pioni.
Ma ti serve qualcosa che ti discerne diciamo, i valori dei momenti angolari qui, quindi la quantità di moto chiaramente si conserva nel decadimento, però non ti aiuta in questo caso. Allora, vi basta guardare come abbiamo concluso il caso A prima. Nel caso A abbiamo fatto una verifica alla fine, e cioè verificare appunto che la funzione d'onda fosse simmetrica, trattandosi di bosoni indistinguibili. Allora, la risposta è questa. Nel primo caso l'abbiamo verificato, adesso invece lo sfruttiamo questa informazione, perché sappiamo che abbiamo un sistema di tre bosoni identici. Quindi adesso imponiamo noi che la funzione d'onda totale deve essere simmetrica, e questo ci darà la risposta. So, for the spatial part, we have -1, L dot, so L12 plus L3. This is for the spatial. Then we have for the spin, -1, total spin. Okay, and this is for the spin component of the wave function for identical boson. Okay, so this is going to be -1, L12 plus L3. If this, you can also write L dot. Okay, forget about this. This is just L dot and then S dot. Okay, and then this we can decouple afterwards. And then the total spin, again, we are talking about pions, so this is 0. And now this must be equal to 1, to +1, because we want the wave function to be symmetric. And so the only possibility is that L12 plus L3 is even. And so the solution is this one. And so we can write that Cp of the pi0, pi0, pi0 state must be -1. Ok?
Ok.
Bene. Andiamo adesso, cos'è l'ultimo? No, ce ne sono ancora altri due. Questo l'abbiamo fatto, andiamo al 2.6. Ok. The pseudoscalar meson eta 0 has quantum numbers JPC 0 minus plus and full width at half maximum lambda 1.3 kilo electron volt keV. Determine its lifetime and which fundamental interaction induce this decay, and then say if the following decays are allowed or forbidden by the conservation laws. Allora, torniamo di là. Questa è la pagina 8. Problema 2.6. Allora, prima cosa dobbiamo capire che tipo di interazione regola questo decadimento. Quindi stiamo considerando il caso di un eta 0 che decade in pi 0, pi 0. Allora, cominciamo, diciamo, al punto A. We know that the decay time is equal to h bar c divided by gamma times c. We now substitute. So this is again 200, or if you like 197, MeV time Fermi. And then now we have the width of 1.3 10 to the minus 3 MeV. And then the speed of light, 3 10 to the 23rd Fermi per second. And this turns out to be of the order of 5 10 to the minus 19 second. So again, a question for you: what kind of interaction can regulate this decay if the decay time is order 10 to the minus 19?
Is it electromagnetic interaction now?
Exactly, yes. Cannot be strong because it is too low, of course, too slow. In average, weak decays are even lower, much lower actually, order of magnitudes. So this is the typical range of electromagnetic processes for decays in this case, okay? So electromagnetic decay. And so also here, we know that parity and charge conjugation must be conserved. So this was the first question. Let's now solve the first one. So we go for the decay eta 0 into pi pi, okay? So we know from the text that JPC is equal to 0 minus plus. And so here we can learn a lot. So first of all, we know that the initial angular momentum must be 0. The initial charge conjugation must be +1, and the initial parity must be -1. Okay. Now, again, angular momentum conservation requires that also the final state angular momentum is the same, so it's also 0. Since the decay is into pions and pions are spinless, again, we only have the orbital angular momentum that is 0. What about now the final state charge conjugation? This is the charge conjugation of the pi0 system, and as we have seen, pi0 are eigenstate of C with eigenvalue +1. So this is +1 squared, that is a +1. And so it is the same as the initial one. Okay, CF is equal to CI. What about parity? We have -1 L pi pi times intrinsic parity of the two pions. This is -1 to the 0 because the orbital angular momentum is 0, and then as usual the intrinsic parity is as negative for pions. So this is a +1, and then overall this is a +1. So again, sorry. So we have a problem, right? Because the initial parity was negative and the final state parity is positive. So that means that this decay is forbidden by conservation law because parity will not be conserved, and we know that it must be conserved because it is an electromagnetic process. Okay, so in fact this decay cannot occur in nature, and the branching ratio of this decay, the measured one, is we have an upper limit, is order of 3.5 10 to the -4. Okay, so this is forbidden. By parity violation in electromagnetic process. Okay. Let's now consider the second case. So the second case is where the eta 0, goes into 3 neutral pions, pi0, pi0, pi0. So let's now solve the B2 case with eta 0. Okay, let's go here. Pi0, pi0, pi0. Again, the quantum numbers are the same. So JPC is equal to 0 minus plus the quantum numbers of the eta 0. And so we know that JI is equal to 0, CI is equal to +1, and PI is equal to -1. So we enforce orbital angular momentum conservation. So the final state angular momentum is, let's say, L dot plus S dot. Total spin is 0, and total angular momentum we can decompose into L12 plus L3, and this must be 0, okay, because of angular momentum conservation. What about now the final state charge conjugation? Now we have a system of 3 pi zeros. Each of them is eigenstate of charge conjugation with eigenvalue +1. So this is +1 to the third, that is +1. And this is again fine. So the final state and initial state charge conjugation eigenvalues are the same. What about parity now? PF is equal to -1 L12 times -1 L3 times the intrinsic parities of the 3 pions. That is -1 L12 plus L3 times -1 to the third, which provides an additional minus sign. So we have -1 to L12 plus L3 plus 1. That is -1 to the 0, as we've seen, plus 1. That is -1. So in this case, we obtain the same parity as the initial state, so parity is conserved, charge conjugation is conserved, and so the decay is permitted. And by comparison, the branching ratio for this decay is quite high, is order of 0.326. So it's about 32%. So in 32% of cases, the eta 0 decays into 3 neutral pions. Okay. Let's move on to the last problem. So consider the strong reaction pi minus with into a deuterium that gives a neutron pair, where the pi minus is captured by the deuterium nucleus in a p wave. Knowing that the intrinsic parity of deuteron is +1, show that the two neutrons must be in a singlet spin state. So this is a little bit more elaborate. Let's move back to the blackboard, whiteboard, pagina 9. Problem. Questo cos'era? 2.7. Okay. So let's first calculate the parity of the initial state. So the parity in the initial state is given is essentially the parity of the pi minus d system. That is -1 to the L times intrinsic parity of the pi minus times intrinsic parity of the deuteron nucleus. Okay. Now we know that the neutron is captured by the deuterium nucleus in a p wave, so the pi deuterium system is in a p wave. That means L equal to 1. So we have -1 to the 1. This is p wave times the intrinsic parities. For the pion, we know it is negative, and from the deuterium, we know from the text that it is positive. So we have -1 times -1 that gives us a +1. So this is the parity in the initial state. Now, since the reaction is regulated by strong interactions, as it is explicitly written in the text, of course, parity must be conserved. So we expect also that the parity in the final state must be 1. So for the final state, we have the parity of the neutron-neutron system, that is -1 to the L and N times intrinsic parity of the two neutrons. This is -1 to the L and N times neutrons are both fermions, so they both come by convention with a positive intrinsic parity. So this is just -1 to the L and N, and we impose that this must be +1 because it is a strong process and parity must be conserved. Quindi must be +1. And as a consequence, we learn that the values of n, L, and n can only be even values. So it can be 0, 2, 4, etc. So even. Okay, so we learn this condition by simply applying parity conservation in this strong decay. Now, what about the final state of this reaction? We have two neutrons, so we have two identical fermions. And so we have to ensure that the total wave function is antisymmetric for exchange of the two fermions, okay? So we know that the psi and n, which must be antisymmetric, this we can, as usual, split into a spatial and a spin component. Okay, and overall, the symmetry of this wave function must be negative, so antisymmetric, okay? So the symmetry is going to be -1 of the n of the neutron system for the spatial part, -1 of s plus 1 for the spin component. So this is the spatial component, and this is the spin component of the wave function. Okay, now this we can write as +1 because ln is odd, is even, sorry, it can only be an even number. So this by sure must be a +1 times -1 s plus 1. And this must be equal to -1 because we want the wave function to be antisymmetric. And so this is only possible if s plus 1 is odd. And so this is only possible if s is even. Okay? And the only way an S-even combination, two, let's say, spin 1/2 particles can be in fermions, can be in an even combination, is that S is equal to 0. In the sense that two spin 1/2 particles, such as neutrons, can never combine to get S equal 2 or S equal 4, whatever, okay? So S equals 0, and so this is, in fact, the spin singlet state. If you remember, this we can write as 0, 0 as 1 over square root of 2, spin up for the first one, spin down for the second, minus spin 1 for the first one, spin down for the second. And if you remember, this is a completely antisymmetric under exchange of one particle 1 with particle 2. So neutron 1 with neutron 2. And in fact, if we just apply here the exchange operator, I, this is chi, so over chi 1, 2, this gives us chi 2, 1, that is 1 over square root of 2 of 2 up, 1 down, minus 2 down, 1 up. That is, we can also write as 1 down, 2 up, minus 1 up, 2 down. That is, in fact, minus chi 1, 2. Okay? So by applying conservation of parity and imposing the antisymmetrization of the wave function, we realize that S can only be even. And so since we have a system of two spin 1/2 particles, S can only be 0. And so in a singlet spin state. E questo risponde quindi alla domanda. Ok? Ci sono domande in generale su questi problemi?
No, per me non ci sono problemi.
Benissimo. Allora facciamo 5-6 minuti di pausa, ricominciamo alle 12:15.
Va bene.
Ok.
Sì.
Va bene.
A dopo.
Grazie.
A dopo. Ok, riprendiamo. Allora, adesso passiamo alle slide e cominciamo un nuovo capitolo, che è il modulo 5, che è la prima parte. Il modulo 5 riguarderà sostanzialmente un grosso capitolo che riguarda appunto lo studio degli hadroni. Cominceremo con questa prima parte che riguarda i numeri quantici di isospin e strangeness, e poi ovviamente proseguiremo con tutto il resto. Ok, so, mi sentite, vero?
Sì, io lo sento.
Benissimo. Okay, so let me go back for a while about symmetries and transformations. Okay, so each strongly interacting particle, that we call hadron in general, is characterized by its mass and by several quantum numbers, which are conveniently divided into two main categories. So the first one is space-time quantum numbers, angular momentum, parity, and charge conjugation, in case the hadron is an eigenstate of C. Okay, and these quantum numbers are denoted either as JP or JPC in the case where the hadron is also an eigenstate of G, of charge conjugation. And the other, if you remember, the other category is the internal quantum numbers. So those that are not associated with the motion or with the spatial properties of the wave function. And these are electric charge, baryonic number, and all the flavor quantum numbers, that is the spin, isospin, strangeness, charm, beauty, and truth, as we will study next, okay, which reflect the flavors of the quarks. Now, the internal quantum numbers are additive. So their values for a given hadron, let's say a baryon or a meson, can be obtained by adding those of the quarks and antiquarks that constitutes the hadron. Here, of course, we are only considering the so-called valence quarks, so only those quarks that, in fact, altogether form the quantum numbers of the hadron. As we will study, and as you already know, inside any hadron, so for instance, inside the proton, there are not only the 3 valence quarks, up, up, down, but also infinite numbers of quark-antiquark pairs and gluons, which fluctuate, okay? So this is the C quarks. This we will study, of course, in the QCD part. So let's now start with the isospin. So I'm sure this you already know from the past years, but let me just go through this. So the strong force is independent of the electric charge. And the experimental evidence derives from the equivalence of the proton-proton, neutron-proton, neutron-neutron interactions once all the Coulomb effects are subtracted. Okay. So if you're able to subtract the electromagnetic effect of these interactions, then the strong force is the same for all these systems. Okay, so it is in fact independent of the electric charge. Now, historically, this equivalence was deduced from the remarkable similarity in the energy level of some mirror nuclei, where mirror nuclei are those nuclei with a neutron replaced by a proton or vice versa. So just have a look here at this energetic level of several nuclei. So in the bottom, we have the nitrogen 15 and the oxygen 15, which are indeed the mirror nuclei. In one case, we have 7 protons and 8 neutrons. In the other case, we have 8 protons and 7 neutrons. And if you look now at the structure and also the wave of the quantum numbers of this energy level, they are very, very, very similar. Another pair is this one, oxygen 17 with fluorine 17. Again, the similarity is remarkable, okay? Not only in the assignment of the quantum numbers, so spin and parity, but also on the energy levels. If instead you take another nuclei, such as oxygen 16, which is not mirror, okay, then you get a completely different pattern of energy levels, okay? So the energy spectra of mirror nuclei are indeed very similar. They show the same pattern of energy level, the same spin and parity quantum numbers. And of course, we do have some differences. They are not identical. And these small differences are only due to electromagnetic effect. So nothing to do with the strong force or the nuclear force. So in other words, if we swap protons and neutrons, the strong force essentially does not notice it. Okay. Once we subtract all the, of course, electromagnetic effects. Now, as you know, protons and neutrons can be regarded as two different charge states of a single strongly interacting object that we will call nucleon, capital N. So the nucleon essentially is a twofold state with the proton and the neutron, where essentially the only difference is the electric charge. We can introduce a new quantum number, which is the isospin I, such that the nucleon is assigned an isospin I equal to 1/2, and then the proton and the neutrons are distinguished by the third component, I3, of this isospin. So for the nucleon, we have 1/2, and then we distinguish the two just by the third component, which is, by convention, plus 1/2 for the proton and minus 1/2 for the neutron. So we can also represent here, in this axis, we have the third component of isospin, okay? So the neutron is minus 1/2, and the proton is plus 1/2. Now, the electric charge is related to the third component of isospin through this simple relation. So for instance, for the proton, you put a plus 1/2 here, you get 1/2 plus 1/2 give you 1, and you exactly get, in absolute value, the charge of the electron. For the neutron, you put a minus 1/2 here, so this goes to 0, and in fact, the charge of the neutron is 0, okay? This, of course, applies to any hadron that it contains up and down. See?
A question. Why are we talking about a third component of the isospin that is a quantum number?
Because this, as we will see in the next slide, this appears as a vector with 3 components, I1, I2, I3. This I will show you in a moment, in 5 minutes.
Okay, thank you.
Essentially is like the spin. And in fact, the algebra of isospin and spin is the same. The spin, you have overall spin 1/2, but then you have the 3z component, right? The 3 component along x, along y, along z, and this is exactly the same.
Okay.
Now, if a scattering or a decay process proceeds through the strong interaction, then both I and the third component of I are conserved. If it proceeds through the electromagnetic interaction, then only the third component of isospin is conserved, but I is violated. And the processes regulated by the weak interaction, as usual, violate anything. So they violate both I and third component of isospin. We'll come back to these, of course, in the next lessons. Now, a clear manifestation of the isospin symmetry is the closeness of the proton and the neutron masses. So as you know, the mass of the proton is order 938 MeV, 0.3 something, and the neutron 939 point something, 0.5 something, okay? So the difference in mass between the proton and the neutron is order of 1 MeV, 1.3 MeV, okay? So it is, of course, relatively small compared to the mass itself of the proton and the neutron. And this small mass difference arises only from a Coulomb energy term. That means by the electromagnetic interaction between the pairs of quarks. Now, apart from their charges, protons and neutrons have, as we've just seen, slightly different masses, which arise from electromagnetic effect. It's an electromagnetic interaction term in the, that provides the different mass. So the isospin symmetry is not an exact symmetry of nature. Okay, we say that the isospin symmetry is a slightly violated symmetry of nature. It would be completely exact if the mass of the proton and the neutron would be exactly the same, but they are not. However, the mass difference is small compared to the proton mass or the neutron mass. And furthermore, the electromagnetic interaction, which is responsible for this difference, is, as you know, only 2 orders of magnitude weaker than the strong interaction. Therefore, the isospin symmetry is a fairly good one. So it is not exact, but still it is a fairly good one. It is only slightly broken. And the level of breaking is just given, you can compute by the difference of the proton neutron mass divided by the proton mass. That is order of 1 per mil. Okay. So we can say, roughly speaking, that the isospin symmetry is a very good one, and it is only violated at the level of the per mil. Now, this was about protons and neutrons, but of course, at fundamental level, the strong interaction occurs among quarks. And the valence quark count of the proton and the neutron, as you know, is up, up, down for the proton and up, down, down for the neutron. So the isospin of protons and neutrons can be derived from that of the valence up and down quarks. Okay, so here we have a similar system. For the up and down quarks, they both come with isospin 1/2, and then they are distinguished by the third component, which is plus 1/2 for the up quark and minus 1/2 for the down quark. So you have say a specular system, okay? So you can also represent again in this axis the third component of isospin. You get -1/2 for the down quark and +1/2 for the up quark. Now, how can we combine these into hadrons? So for any state composed of quarks and antiquarks, one has that the third component of isospin is given by this simple formula. So it's 1/2 Nu minus Nd, where Nu is in turn the difference between the number of up quark minus the number of anti-up quark, and Nd is the difference between the number of down quark minus the number of anti-down quark. So for instance, if you apply this formula for the proton, we have 1/2, we have 2 up quarks, we don't have any down quark, any anti-quark, of course, as a valence quark, and then we have only 1 d quark. So 2 minus 1 gives us +1 times 1/2, we get +1/2. For the neutron, instead, we have only 1 up quark and 2 down quark. So overall, we get a minus sign here, so -1/2. And this, of course, you can apply in general for any hadron, okay? And of course, this only makes sense for hadrons that contain some up or down quark as a valence quarks. Now, more in general. We have already introduced global transformations of the form U alpha e to I alpha, depending on a single real parameter alpha, forming, if you remember, a unitary group U1. Okay. Now, the isospin transformation are a unitary global transformation of this form here, e to the minus I half theta I ti, where U is again a unitary operator. So let's look into more detail here. So the theta I are called the parameters of the transformation, as we have seen for rotations, for instance, okay? And the tau I are the generators of this transformation, which are conventionally chosen to be exactly the Pauli matrices. So the same you use for the spin, okay? So T1, T2, T3. Now, in general, the set of all unitary 2x2 matrices form a U2 group, okay, which is an extension of the U1 group we saw before. But the Pauli matrices have 2 additional properties. That is that the determinant is equal to 1 and the trace is equal to 0, where the trace is the sum of the element in the diagonals, okay? And so given these 2 additional properties, they form a subgroup of U2 that is called a special unitarity group. So special unitarity matrix SU2, where S stands for special, okay? Of course, they are global transformation. As you see here, the parameter of the transformation does not depend on the space-time coordinate. So they are global, okay? So we say that isospin transformation form an SU2 group and that isospin symmetry arises from the invariance of the Lagrangian of strong interactions, so the Lagrangian of QCD, under SU2 isospin global transformations, okay? So this is the sense of the isospin symmetry. It means that the Lagrangian of the strong interaction is symmetric under these SU2 global transformations. Now, in general, SU2 matrix are the form of this form here. So A, B minus B star, A star. This means a complex conjugate, where A and B are complex numbers such that the sum of their moduli gives 1. How can we generalize this? So in general, the dimension of a special unitary group, SUN, is given by n squared minus 1. So for the case of SU2, n is equal to 2. So 2 to the square gives 4, minus 1 gives us 3. Okay? And in fact, SU2 transformation depend on 3 parameters, theta I, and 3 generators, which are the 3 Pauli matrices. Similarly, if we have SU3, then we, based on this formula here, we're going to have 8 parameters and 8 generators, and this is the case of QCD, for instance. And then we can also have higher rank special unitarity groups, such as SU5, which is for unified theories, as we'll see at the end, etc. Okay. Now, but still on the language of group theory, more precisely, we say that the Pauli matrices constitute a fundamental representation of SU2. The basis for this representation is conventionally chosen to be the eigenvectors of tau3, which are simultaneous eigenvectors of the third component of isospin and the isospin squared. And we can choose this basis to describe the up and down states, or equivalently, the proton and the neutron isospin states. Okay, so for up, down, or for proton, this eigenstate will be 1, 0. And for the down quarks or the neutron will be 0, -1. So let's now show that this, in fact, corresponds to having the up and down quark are eigenstate of isospin with eigenvalues +1 e -1. Quindi torno adesso fuori da qui. Qui mi sa che si è disconnessa la lavagna. Proviamo a riconnetterla. Mi sa che devo proprio chiudere e riaprire. Lo vede? Boh, vediamo un po'. No, faccio prima chiudere e riaprire. Scusate, datemi un attimo. Ok. Ok, ci siamo. Quindi questa è la pagina 10. So we have just defined the eigenstate, the isospin eigenstate of the up quark as 1, 0, and for the down quark as 0, 1. So let's show that these are indeed the eigenstate of T3, tau 3, so the third Pauli matrices. So we apply these to the up quark state. It is 1, 0, 0, -1, acting on 1, 0 on our state. And if you take just the product of this matrix times this vector, you indeed obtain 1, 0, trivially. That is +1 u. If, on the other hand, you apply the third Pauli matrices on the down quark isospin state, that is 1, 0, 0, -1 over 0, 1 now, then you obtain 0, -1, that is -1 times 0, 1, that is -1 d. All right. So back to the slide. We have seen that up quark, or equivalently the proton state, which is 1, 0 in the isospin space, is eigenstate of tau 3 with eigenvalue +1, and the deuteron, or equivalently, so the down quark, or equivalently the neutron state, which is 0, 1, is eigenstate of T3, but now with eigenvalue -1. And let me note you again that this is the same notation used for spin up and spin down for a spin 1/2 particle. So as you know already from quantum mechanics. Now, in general, the isospin transformation that we just showed before are not just the symbol interchange of an up and a down quark or a proton with a neutron, which is in fact what we see in nature, but more in general, it represents rotations in the abstract isospin space. And in fact, the parameters theta I can be regarded as the 3 Euler angles in this abstract isospin space. Okay. So the rotated, in general, U prime and D prime quark appears a linear combination of the unrotated U and D quarks. So let's see why. So these are our unrotated state, where rotated means rotated in the isospin space. Okay. So up down, we apply our rotation matrix in isospin space. We take the product, so in general, we're going to have this kind of combination. So U prime is equal to U11U plus U12D, and D prime is equal to U21U plus U22D. Okay, so we're going to have this kind of combination of the rotated up and down isospin states compared to the unrotated ones. Now, what is the problem here? The problem is that if isospin symmetry were exact, and so up and down quark were indeed indistinguishable, this would be perfectly fine, perfectly acceptable. However, we know that up and down quark have different electric charge, okay, and also slightly different mass. So the linear combination above would lead to a non-conservation of electric charge. Consequently, it turns out that the only physically meaningful isospin transformation is indeed the one corresponding to a pure U to D exchange, which in turn corresponds to rotating of plus pi or minus pi the up and down states in the two axes. So let's also show this in the board. Quindi questa è la pagina 11. So, the rotated isospin up quark state, okay, is obtained from the unrotated by applying the isospin transformation, where theta is exactly plus pi, and then we have the second Pauli matrix here. So let's show why this is the case. So this we can write as e to minus I pi divided by 2 tau 2 u. Now this you can decompose using the Euler formula as cosine of pi half I minus I tau 2 sine of pi minus acting on the up quark, the unrotated up quark isospin state. So now we substitute. So the cosine of 90 degrees is 0, clearly. So this is 0 multiplying the identity matrix minus I. Then we have the second Pauli matrices, 0 minus I, 0. The sine of 90 degrees is 1. And then we're acting on our unrotated up quark state. So this first term cancel, and we're just going to have here 0, minus 1, 1, 0, acting on 1, 0. And when you now take the product of this matrix with this vector, you would obtain immediately 0, 1. That is, in fact, the D state. Okay? So the rotated up state is exactly the down quark state. Let's do the inverse. So we start now from the rotated D prime, the D isospin state. That is e to the minus I half, now rotated by minus pi along the two axis direction, acting on the unrotated D isospin state. That is e to the minus I minus pi half tau 2 D. That is cosine of minus pi half I minus I tau 2 sine of minus pi half acting on D. That is, again, the cosine goes to 0, 1, 0, 0, 1, minus I. Here we have again the second Pauli matrices, 0, minus I, 0. The sine of minus 90 degrees gives us a minus 1, acting on the deuteron, the down quark state, 0, 1. Scusate. So this goes away. That is I on 0 minus I 0, acting on 0, 1. That is 0, 1 minus 1, 0, acting on 0, 1. And now when you take the product of this matrix with this vector, you obtain 1, 0. So the up state. So the rotated of the up quark is the down quark, and the rotated of the down quark is the up quark. Ok. Se ci siete tutti possiamo passare alle slide.
Ok.
Okay. Now, in the language of group theory, isospin 1/2 particles, such as the proton or the neutron or the up and down quarks, constitute so-called isospin doublets. Okay. So a first doublet is the neutron, which is a proton-neutron state, and the other doublet is the one constituted by the up and down quark. And in general, an isospin multiplet contains 2i plus 1 members of similar masses. So in this case, I is equal to 1/2. So we have just 2 members. So these multiplets are just simply doublets. And in fact, they both, the states of these doublets are essentially with the same mass, the only tiny difference in the mass. Now, back to the question of your colleague before, we can now write the component of the isospin vector in terms of the 3 Pauli matrices divided by 2. Okay, so we can now write the isospin transformation where now we have just IE here, II, sorry. So the 3 generators of the isospin transformation, which are rotation in the isospin space, are expressed in terms of the 3 component of the isospin vector. Okay, so this is exactly what you have, in fact, for spin. Okay, you have your spin vector, and then you have your 3 projections along x, y, and z directions. Okay, so indeed they follow exactly the same computation algebra of the 3 component of angular momentum in general, which we call the Lie algebra. No, sorry, Lie algebra. I think the correct pronunciation is Lie algebra, which are the generators of rotation in ordinary space. Okay, so we have the same kind of commutation rules that we have already for angular momentum or for spin, okay, where epsilon jkl is the standard Levi-Civita tensor, okay, which is a totally antisymmetric tensor, and so explicitly you have this permutation rule for the various components. Okay, so this is exactly the same as spin and as rotation, so orbital orbital momentum, angular momentum, sorry. Now, since isospin has the same algebra of spin, the isospin states of a system of 2 light quark can be written in a complete analogy with the combination of 2 spin 1/2 state. So let's now see how we can combine system to get isospin bound states. Okay. So since the algebra is the same, we can combine up and down state in the same way we can combine spin up and spin down state for the spin case. So also in this case, for 2 light quarks, we want to have a singlet state with isospin, total isospin equals 0, which is completely antisymmetric under U and D exchange, and 3 states which form a triplet state, which are now completely symmetric under U with D exchange. So this is in perfect analogy with what we know from spin, from quantum mechanics. Okay. In the language of group theory, we say that 2 isospin doublets decompose into an isospin 0 singlet and an isospin 1 triplet. And the symbol, so symbolically, we write this in this way. So these are the 2 isospin doublets, and they decompose in an isospin singlet and an isospin triplet. This is the way you would write this in a group theory. Okay, so this is the triplet with the total isospin equal to 1, and the 3 projections are -1, 0, and +1, and these are the combination of corresponding combination of up and down quark. And this is the singlet, which is antisymmetric, which comes with total isospin 0, and of course also the third component is also 0. Now, what about baryons and mesons? So let me start with baryons. Baryons, as you know, are bound state of 3 quarks, and a system of 3 isospin doublets decompose into an isospin 3/2 quadruplet and 2 isospin 1/2 doublets. So again, back to group theory. If you want to construct the isospin states of baryons, okay, you have to consider all the combination of 3 quark doublets, and this results in a quadruplet with isospin 3/2 and 2 doublets with isospin 1/2. So this we can also visualize here. So this is the quadruplet. So we have in fact 4 states, all with similar masses in general. And so the eigenvalue of the third component are -3/2, -1/2, +1/2, +3/2. And then we have the two singlets, okay? They both come with I equal 1/2, but they have different combinations, as you see here, of up and down quarks. What about now the symmetry properties of these states? They are different, okay? So as we've seen before, let me go back here. We've seen that the singlet, if you combine two quark doublets, you get a singlet which is completely antisymmetric and a triplet which is completely symmetric for exchange of up and down. What about now these more complicated states of the baryons? In this case, it turns out that the quadruplet state is completely symmetric under interchange of any two quarks. You can just try yourself, okay? But the two doublets are either in a mixed symmetry or in a mixed asymmetry case. What does it mean? For the first one, mixed symmetry means that this state is symmetric only under exchange of particle 1 with particle 2. The first with the second. Whereas the second doublet is antisymmetric only under the exchange of the first particle with the second particle. So mixed symmetry and mixed asymmetry states have no definite symmetry under the exchange of the third with the third, the first with the third, and the second with the third particle. So it's a mixed state, in fact. And this will become relevant, as we will see in the next lessons when we want to calculate the wave function of the proton, for instance, of baryons in general. Okay. Now, what about antiquark? So we're talking about the quark isospin doublet. So the antiquark isospin doublet is conventionally defined in this way. So the top particle is minus anti-down quark, and the bottom particle is the the anti-up quark. And this definition with this minus sign is not, of course, casual, but it is such that both quarks and antiquarks transform exactly in the same manner if you use this definition for the antiquark isodoublets under the isospin transformation. So you're going to have exactly the same kind of isospin transformation for quarks and antiquarks if you define the antiquark isodoublet in this way. And as a consequence, physical predictions, if you make this convention here, are invariant under simultaneous up-down or anti-up, anti-down transformations. So what is now the situation for the antiquark isospin doublet? Okay, so in this case, it is the minus anti-down quark that comes with the positive value of the third component, and the anti-up quark comes with the negative value. So when you represent now the antiquark doublet in the I3 axis, you see that the minus d bar takes the value +1/2, and the u bar takes the value -1/2. And this has to be compared with the situation with quark, where instead the up quark has the positive projection and the down quark has the negative projection. We will come back to this later on. So this was about baryons. What about mesons? So mesons, as you know, are q bar bound states, so bound state of a quark and an antiquark. And the four possible isospin states of light mesons are obtained from the combination of an SU2 quark doublet and an SU2 antiquark doublet. You now want to compare, you combine a quark with antiquark isospin doublets. And then one obtained the following states. So an isospin triplet state and an isospin singlet state, defined in this way. Okay. So the difference with respect to what I was showing before, let me go back here, is that this was only for quark doublets, up and down. There are no antiquark here. Now we also define the way the antiquark isodoublet transform, and so we can now combine a quark doublet with an doublet, yes, with an antiquark doublet. And when you do so, you obtain these states. One is a singlet and one is a triplet. The singlet state now is symmetric under simultaneous exchange of d with u and d bar with u bar. And the triplet state is antisymmetric under simultaneous exchange of d with u and d bar with u bar. So back to the group theory language, okay? When you combine a quark doublet with an antiquark doublet, you obtain a singlet times plus a triplet state, okay? And these are now how they are located in the third component isospin axis. And these are the different combination of up and down quarks in the two cases. Now, as we shall see, the triplet state corresponds to the 3 pions. And this is what we see today. And then the singlet state turns out to be a mixture of the eta and eta prime mesons. And this we will study, of course, next. So let me now spend how much? Quanto tempo abbiamo? Abbiamo 10 minuti, ok. Quindi adesso facciamo gli ultimi 10 minuti, facciamo un po' un richiamo della teoria di Yukawa e vediamo come si sono ricavate le proprietà di spin e isospin dei pioni, ok. So back to Yukawa. So the pi meson, or pion, as we already said, was originally predicted by Yukawa in 1935 to be the mediator of the nuclear force. That is the force that keeps the nucleon bound against the Coulomb repulsion among protons. And the nuclear interaction was described by Yukawa in terms of this potential here, okay, where R essentially is the inverse of the mass of the exchanged boson. Now, given the experimental evidence that the range of nuclear forces is of the order of 1 Fermi, that is the size of the proton essentially, or light nuclei, Yukawa predicted that the mass of the exchanged boson must be of the order of 100 MeV. This we already discussed in the past, okay? Now, some more details. So in 1936, so 1 year later, a penetrating charged particle with a mass of the order of 100 MeV was indeed discovered in the atmospheric showers generated by cosmic rays. And of course, this was immediately associated to be the Yukawa meson. But it was a big mistake instead. Because in 1947, so more than a decade later, a famous experiment performed by Conversi, Pancini, and Piccioni demonstrated that this particle is not absorbed when passing through a layer of material. But if it were the Yukawa particle, it should have interacted so strongly with the nuclei in the material to be absorbed immediately, well before the decay time, okay? In a time much shorter than the decay time. So something was wrong here. And in fact, it turned out that the particle discovered in 1936 was the muon. The muon is a lepton. It has nothing to do with the pion or with the Yukawa particle, of course. It's just identical to the electron, but order of 200 times heavier. So the mass of the muon is 105 MeV compared to the mass of the electron, which is half an MeV. Now, the pion, so the Yukawa particle was finally observed in 1947 by Occhialini and Powell, again in cosmic showers, by exposing emulsion stacks at an altitude of 5,500 meters in the Andes in South America. So what they observed? They observed a new particle with the mass again of the order of 100 MeV, but now decaying into the penetrating particle that was observed in 1936. So this new particle was indeed observed to decay into the muon. In addition, they also observed that the energy of the muons was always the same, indicating a two-body decay into a muon plus something else that was not observed. So clearly was a neutral particle that was, as we know today, later recognized to be the muon antineutrino. Okay. So in 1939, the complete decaying chain was captured in a high sensitivity emulsion. So essentially, they saw the track of the incoming pion. Then the pion decayed at some point, so they observed the track of the muon, and then the muon decayed, so they also observed the electron, which is the final state decay of the charged particle of the muon. Okay. So today we know that this decay chain is a bit more complicated. Okay, we have neutrinos. This is regulated by the weak interaction. This, of course, was what not known at the time. And today we know that the pi plus goes into mu plus plus mu neutrino, the same for the pi minus into mu minus with the mu antineutrino. And then in turn, the mu plus decays into a positron, electron neutrino, and muon antineutrino. Or equivalently, the mu minus goes into electron antineutrino, and muon neutrino. This we will study, of course, later on in the course when we will introduce the weak interactions, okay? Now, since according to the Yukawa theory, the pion should mediate the proton-proton, but also proton-neutron, and also neutron-neutron interaction, then it was expected that the neutron, so these Yukawa particles, should come with 3 different charges, the pi plus, pi 0, and pi minus, okay? And the final proof that the observed particles were indeed the Yukawa meson came with the observation of this nuclear reaction, okay, where we have an incoming pi plus or pi minus with the nucleus. And the result, so the pion interacts strongly now with the target nucleus, transforming a proton into a neutron and vice versa, okay? So, for instance, the final state nucleon has the same Z. So one neutron was expelled and transformed into a proton, and vice versa here, okay? And this, of course, is only possible if the pion is indeed strongly interacting. And so finally, this was proven to be the particle predicted by Yukawa, okay? Of course, today we know that at fundamental level, the nuclear force is just a residual force of the more fundamental strong force that occurs between quarks, and it is mediated by gluons, which are, as we will study, the gauge bosons of the strong interaction of QCD. Okay, so this is now the modern view, of course. Now, still on the properties of the pions, the properties of pions could be systematically studied with the advent of the first particle accelerators. And in fact, the first accelerator with sufficient energy to produce pions was this 184-inch Berkeley cyclotron, which could accelerate alpha particles up to 380 MeV. So how did they measure the mass of the pion? Okay, so the mass of charged pion was measured using the relation, essentially the inverse of the relativistic relation between mass, momentum, and energy, okay? So they had to make a simultaneous measurement of the energy and the momentum. The momentum was measured through the radius of curvature, R, of the charged tracks inside the magnetic field, known, okay? So you probably know that if you express the momentum in J/C, the radius in meters, and the magnetic field in Tesla, then you get this very simple relation with this additional factor 0.3. Okay, this gives you exactly the momentum once you measure the magnetic field in Tesla and the curvature radius. And the energy that you also need here was measured by measuring the range inside the emulsion bricks. And they found these values, so 131 MeV for the pi plus, essentially the same for the pi minus, okay? So let me compare you now these historical values with the present values, okay? So you see now, of course, the precision is much, much higher, okay? These are for the pi plus and pi minus, which indeed have been shown to have exactly the same mass. This is another proof of the CPT theorem. This is the mass of the neutral pion, which is slightly lighter. So it's 140 with 135, essentially, MeV, okay? And the lifetime of charged pions could only be measured after the advent of the first detectors with fast electronics, okay? And with a time resolution of the order of nanoseconds, okay? And when this was possible, of course, one could also measure precisely the decay time of both the charged pions and the neutral pions. So for the charged pions is of the order 2.610 to the minus 8 second. As you see, this time is much, much longer than the strong decays and also the electromagnetic decays. So this is typical of a weak decay, okay? Whereas if you look now at the pi zero, we get a decay time which is much, much, much shorter, okay, 9 orders of magnitude. And it is indeed typical of the range of electromagnetic interaction. So the pi zero decays electromagnetically into 2 photons, whereas, as we will see, the pi plus and pi minus decay can only decay weakly, okay, into muons plus neutrinos. Okay, this is what I say. So while charged pions decay weakly and those are relatively slow, neutral pions decay electromagnetically. Yes, this I said already. So now, the last thing, what about the spin of pions, how it was measured? Today we know that they are spinless, okay? So the spin of pion was measured through the ratio of cross-section for the forward and backward reaction. So here the principle of the tail balance is applied, which is a consequence of the time reversal conservation in strong processes, as we have studied last time, okay? So essentially, they took the ratio of the measurement of the cross-section of these two processes, which has exactly one the time reversal of the other. So in the numerator, we have an absorption cross-section where the pion is absorbed by the deuteron, and this was measured in 1951 using a pion beam of kinetic energy 24 MeV. And in the denominator, it is a production cross-section where now the pion is produced in the final state. This was measured a couple of years later using a proton beam of kinetic energy at 341 MeV. And it turns out that the center of mass energy of the two reactions are almost equal, so you can really make a sensible ratio of the two. Okay. Now, when you take the full expression of the cross-section, as we derived from the Fermi-Golden rule, okay, most of the term cancel, okay, in the ratio. So the transition matrix element, for instance, cancel because the processes are just the same but reversed in time. And the only thing that remains are the spin multiplicities in the final state, okay, and of course the squared momenta for the final state in the two cases. Now, it was known that the spin of the proton is 1/2. It was also known that the spin of the deuteron is 1. So you can also put numbers here and simplify the situation. And the only unknown here is the spin of the pion, okay, once you measure precisely the moment of the proton and the pion, okay. Now, of course, these two, okay, so the only unknown was this denominator here, 2 spin of the pion plus 1, and it turns out that this was consistent with 1. And so that the spin of the pion must be 0. Okay, so this is the way it was measured, that the spin of the pions is 0. Now, as we have seen, the masses of the 3 pions are very close, okay? The charged and neutral pions differ only for a few MeV, which again is only due to electromagnetic effect. And so it is clearly not a surprise to you anymore that the 3 pions form an isospin triplet. So the 3 pions are assigned an isospin equal to 1, okay? These are the corresponding quark-anti-quark states, and these are the 3 projections along the third axis. +1 for the pi plus, 0 for the pi 0, and -1 for the pi minus. Ok, questa era l'ultima slide. Se avete domande, che ore sono?
No, io sono
l'una, perfetto. Ok. Quindi abbiamo introdotto il concetto di isospin, l'abbiamo considerato quindi sistemi protone-neutrone, ma che derivano a livello più fondamentale da sistemi quark-up, quark-down. Abbiamo visto come combinare doppietti di quark o doppietti di antiquark per formare mesoni o barioni, e poi, insomma, studiando anche dal punto di vista storico, diciamo, le proprietà dei pioni, siamo giunti alla conclusione che così come protone e neutrone sono un doppietto di isospin, allo stesso modo pi più, pi 0 e pi meno sono un tripletto di isospin, quindi con isospin uguale 1. Allora, noi continuiamo poi credo, mercoledì prossimo. Non vorrei che ci fosse, datemi un attimino. Noi ci vediamo, sì, ci vediamo il 22, ok. Perché poi il 23 è di nuovo festa San Giorgio. Quindi il 22 andremo avanti con l'isospin e in particolare studieremo come la conservazione, imporre la conservazione dell'isospin nelle interazioni forti ti consente anche di fare delle previsioni molto precise su rapporti di sezioni d'urto. Questo lo vedremo la prossima volta. Ok, bene, se non ci sono domande, allora arrivederci, buon weekend e a mercoledì prossimo.
Grazie
Arrivederci. Buon weekend anche a lei.
Metterò le scansioni della lavagna di oggi, anche queste qui le metterò online quanto prima.
Va bene.
Arrivederci.
Arrivederci.
Arrivederci.